So here we need to talk about a method of taking the limit called L'Hopital's rule. Now, L'Hopital's rule only applies to something called an indeterminate form. Now, you got to understand there's a difference between indeterminate and undefined. Undefined means something doesn't have a value. It never will have a value, no matter what you do. Indeterminate means we don't know what the value is. The value still needs to be determined. And so two of the most common indeterminate forms are 0 over 0 and infinity over infinity. Some people might say this first one is equal to 0, but it's not. Or maybe it's equal to 1, but it's not. This is indeterminate. This could equal anything. It needs to still be determined. And so is infinity over infinity. And you could even do plus or minus on the infinities. It really doesn't make a difference. Positive over negative, negative over positive. It doesn't change things. Any infinity over another infinity and 0 over 0 are the two most common indeterminate forms. So we can't say what they're equal to. So if we're looking at a limit, let's say this limit right here. The limit as x approaches 0 of e to the 2x minus 1 over e to the x minus 1. As x approaches 0, this right here will get closer and closer to 1, okay? Because if this gets close to 0, this gets close to e to the 0, which will get close to 1. Well, this is subtracting 1, so the numerator is going to get closer and closer to 0. Same thing is going to happen in the denominator. And so this fraction, as x gets closer to 0, is going to get closer and closer to 0 over 0. But that is indeterminate. It doesn't have a value to it. We don't know whether it's going to be equal to 5 or 1 or negative 7, whatever. Okay? So we can't really say, based off of just looking at the behavior here, of what the limit will approach. And remember, some limits don't exist at all, right? That doesn't necessarily mean that this doesn't exist either. It could exist, it could not exist, it could be equal to 1, it could be equal to 0, it could be equal to 5. That's the whole idea of what indeterminate is. It could be anything. So how are we going to evaluate this limit? Well, we could do some of the tricks we learned back in Calc 1. One of the tricks you learned in Calc 1 was to factor and simplify before you evaluate the limit. And so if we did that, the numerator could think of as a difference of squares, because e to the 2x is e to the x squared. Power to a power, you would multiply these. And so you would get e to the x minus 1, e to the x plus 1, difference of squares formula, those are conjugates, over e to the x minus 1. It just stays the same. Cancel. So now you have the limit as x approaches 0 of e to the x plus 1. Now as x approaches 0 of this is going to get closer and closer and closer to 1, and therefore I'm going to have 1 plus 1, so 2. So in this case, something that was getting closer to 0 over 0, in actuality, ends up giving me 2. Look at this next one. The problem with this one is factoring the numerator doesn't do anything to help you. If you look at what happens as x approaches 0, the numerator, again, is going to approach 0. The denominator is just x, which is approaching 0. This one's getting closer and closer to this indeterminate form as well. But factoring is not going to help you here. You can factor that just as well as we did before, but nothing's going to cancel because of what the denominator is. So how are we going to go about doing this one? Well, think about some of the other things you did in Calc 1. If there was a root somewhere, you could try and rationalize it. You could use the squeeze theorem or the sandwich theorem, which is extremely complicated, but primarily the way you would have to have done this one, because you really don't have any other options. Graphing it doesn't really give you the answer for the limit. It's an estimate for seeing what the limit looks like it's getting close to. Same thing with making tables. So this is where L'Hopital's rule comes in. So L'Hopital's rule says, all right, let's look at two functions f and g. Let these functions be differentiable, which means you can take the derivative of them on some interval that contains c. Now, they don't have to be differentiable at c, just an interval that contains c. We also have to assume that g prime of x, doesn't equal 0. Because it's going to be in the denominator. All right, that set aside. If we want to do the limit of f over g, so you want to do the limit as x approaches c of this fraction, okay? And that fraction happens to be an indeterminate form, just like the two examples we saw. One way you can evaluate that limit is to really evaluate another limit that will be equal to it. And that limit would be the limit as x approaches c of f prime over g prime. So what we've done throughout calculus is when we're trying to evaluate a limit, usually we can't do that limit directly. What we try and do is evaluate another limit that will give us the answer we want. So, in that last example, it was the limit as x approaches 0 of e to the 2x minus 1 over e to the x minus 1. But instead of doing that, we did the limit as x approaches 0 of e to the x plus 1. We did the limit of this function instead of doing the limit of this function. Now, why can we do that? We can do that because as x approaches 0, these two functions behave exactly the same way. These two functions are equal to each other everywhere around 0, except at 0. And that was the whole thing you learned in Calc 1, of why you can do that. Well, this is basically saying the same thing. If I'm trying to do the limit as x approaches c of f of x over g of x, and that limit happens to result in an indeterminate form, and that's the key. It has to result in an indeterminate form. Right now, 0 over 0, infinity over infinity are the two main ones, but we're going to see a couple other ones too. There's a couple other different indeterminate forms that are ultimately just versions of 0 over 0 or infinity over infinity. But anyway, if we want to do this limit, instead of doing the limit of this function, we're going to then do the limit of the derivative of each function. And the idea here, generally, is that this would give me the same limit that this did. What you do when you take the limit of a quotient is you're ultimately kind of looking at how the numerator and denominator act off one another as you approach this value. And so this will behave generally the same way this one does around a particular value. And this is why L'Hopital's rule works. So if the little tricks you learned in Calc 1 like this, factoring, don't necessarily work, you could always fall back on L'Hopital's rule. Now, you could also skip factoring altogether. I could do this limit that we just did using factoring. I can do that using L'Hopital's rule because it was an indeterminate limit to start with. The whole idea of factoring to get to here doesn't need to work with indeterminate forms, right? You could do that factoring idea for anything, but L'Hopital's rule only works when you have an indeterminate form. The best thing probably would be to get through a bunch of examples. Before I do that, I want to show you just a couple other indeterminate forms. So we know 0 over 0, that's a big one. Plus or minus infinity over plus or minus infinity, that's a big one. And those will be the two most common ones you come across. There's a couple other ones. Infinity minus infinity, that's indeterminate. People might go, well, you're subtracting the same thing from itself. Yeah, but remember, infinity is not a number. Infinity is more of a concept. It's a growing value. It's a changing value. So this infinity and this infinity aren't necessarily the same. So this is why this is indeterminate. 0 times infinity, 0 to the 0, 1 to the infinity, infinity to the 0. These are all indeterminate forms. And you're going to see why they're indeterminate forms, because in the end, they're all versions, essentially, of these two things. When we come up with one of these, we're going to basically turn it into one of these two. So first, back to that one we were talking about, the one we couldn't just factor and simplify. So in this case, if we look at the limit as x approaches 0 of e to the 2x minus 1 over x. Remember, look at what's happening. As x approaches 0, this is getting closer to 0 here. E to the 0 would be 1, so 1 minus 1 would give me 0 in the numerator. In the denominator, same thing. So if this is getting closer and closer to 0 over 0, that's an indeterminate form. Right there, that's an indication of L'Hopital's rule. So if we're going to apply L'Hopital's rule to this thing, we're going to instead do the limit as x approaches 0 of the derivative of the numerator. Now remember, this is not like quotient rule or anything. You're going to do the numerator separate from the denominator. So the derivative of the numerator, here's where you got to make sure you know your derivative rules, would be 2e to the 2x over the derivative of the denominator would be 1. Now if we look at the limit of this, as x approaches 0, this is going to get closer and closer to 0 here. So this will be e to the 0, which is 1. So this is going to be 2 times 1 over 1. The denominator is just a constant. It's going to stay a constant. This is a constant multiple. So we end up with 2. So this 0 over 0 was actually a value of 2. Which you might say, well, that was the same as the last one. So aren't all 0 over 0s going to end up being 2? No. We're going to see a couple that are going to be equal to 1, are going to be equal to 5, are going to be equal to 0. Because 0 over 0 could be anything. All right, let's do another one. So if we look at this limit here. So the limit as x approaches infinity of log x over x. Now it doesn't matter what x is approaching. What matters is what happens to the fraction. So as x gets closer and closer to infinity, the numerator is going to get closer and closer to infinity. And the denominator is just x, so if x is going to infinity, x is going to infinity. And the best way to see this, at least for the log, is remember the graph of a logarithm looks like this. That's your basic logarithmic graph. So as x goes to infinity here, this is x going to infinity, what's happening to the y value? Well, this is going to constantly go up, so y is going to infinity. All right. Well, here you go, L'Hopital's rule, okay? This is an indeterminate form. So what are we going to do? Again, we could try and fall back on some of our Calc 1 stuff, like factoring, rationalizing, whatever. But ultimately, L'Hopital's rule is easier than a lot of that. So we can't factor anyway, but we could take the derivative. Both of these functions are differentiable. So the limit as x approaches infinity of the derivative of log is 1 over x, and the derivative of x is 1. Then I go and say, all right, well, this is 1 over x over 1, which is really just 1 over x, right? And as x goes to infinity, as the denominator of this fraction goes to infinity here, what's the value of the whole thing? Remember, the denominator gets really, really big, the whole fraction starts to get smaller and goes to 0. So this indeterminate form was actually equal to 0. All right, let's go for another one. Let's look at this one here. So if I did the limit as x approaches infinity of x squared over, I'm going to change this. I see there's a typo here. This should be a plus x, e to the x, okay? It's a typo because if it was e to the minus x, it's actually not going to end up being an indeterminate form. So I'm going to change it, e to the positive x. So as x goes to infinity, this is going to go to infinity. As x gets big, this whole thing gets big, right? And the same thing goes with e to the x. Again, just by looking at their graphs, right? Parabola, exponential function. As x goes to infinity, y goes to infinity. As x goes to infinity, y goes to infinity. That's the easiest way to see what's happening with these functions, I think, is for people who are having trouble with this. So anyway, indeterminate, right? Hopital's rule. So what I'm going to do is I'm going to say, all right, well, let's do the limit as x approaches infinity of 2x over e to the x. So instead of doing this, I'm going to do this limit. Now, what happens here? As x goes to infinity, this is going to get bigger, and this is still going to get bigger. What do I have? I have another indeterminate form. Well, I got another L'Hopital's rule problem. Let's just do it again. There's no limit to the amount of times you can apply L'Hopital's rule. The only limit is you can do it when there's an indeterminate form. So the only time you have to stop applying L'Hopital's rule is when this is no longer an indeterminate form. So we do the limit as x approaches infinity of the derivative of the top is 2. The derivative of e to the x is still just e to the x. So now as x approaches infinity, the numerator just stays 2. The denominator, however, is going to keep getting bigger again. It's going to go to infinity. Well, 2 over infinity, the denominator gets big, the numerator stays 2. That's 0. Okay? Some real basic stuff about limits you learned in Calc 1 is that if your denominator grows but the numerator doesn't, the whole thing goes to 0. I want to show you one thing here, is that x squared over e to the x could also be written as x squared times e to the negative x. This is the same thing as this. So if I do the limit as x approaches infinity of this product instead of this quotient, what would happen? Well, first off, we need to look at this as a limit and just see what the behavior is. As x gets big, this is going to get big. As x gets really big here, since this is e to the minus x, this whole thing actually gets closer and closer to 0. Again, look at the graph. This is what e to the minus x looks like. As x goes to infinity, the y value gets closer and closer to 0. Now, this is where I said there are other versions of indeterminate forms. This was one of those ones I said earlier is indeterminate. Now, the problem with this and leaving it like this is while this is indeterminate, it is not a fraction. And L'Hopital's rule only applies to fractional indeterminate forms. So pretty important thing to learn about L'Hopital's rule. So what I would have to do is recognize that yes, while this is indeterminate, some people might say, oh, well, 0 times anything is 0, that equals 0. And you say, well, I would have got the answer right. Yeah, but you would have gotten lucky on this example. If this is indeterminate, it's not always going to equal 0. So recognize that this is indeterminate, and then recognize that this is a version, essentially, of this. And so I would have to turn this into a fraction. The easiest way is to make one of these exponents change its sign. So either make this exponent negative or make this exponent positive, turn it into this, and then look at it as a fractional indeterminate form and apply L'Hopital's rule. All right, so here is another one, very similar to the example I just gave you. Now look at this. As x approaches infinity, this first fraction is going to get closer and closer and closer to 0. The second piece, second function, is going to get closer and closer to infinity. As x gets big, this goes to 0, this goes to infinity. So you have 0 times infinity. Again, indeterminate. So what are we going to do? Well, what we need to do is to apply L'Hopital's rule. We can't look at it that way. We have to look at it as a fraction. So I do the limit as x approaches 0, or infinity, sorry, of square root of x over e to the x. Now, as x goes to infinity, this is going to get bigger, this is going to get bigger, so this is going to infinity over infinity. Now I can apply L'Hopital's rule. So I'm going to write this as x to the negative, x to the 1/2. So I have the limit as x approaches infinity of 1/2 x to the minus 1/2 over e to the x. Those are your two derivatives. Again, really important you know your derivatives, so power rule and e to the x. What I'm going to do is I'm going to simplify this. X goes to infinity. This is to a negative exponent, so it should come to the denominator. The 2 is already in the denominator, and e to the x is as well. So really what this is 2 x to the 1/2 e to the x. It's always better to simplify before you really think about what's happening with x. So now x is going to infinity. This is getting bigger. This is getting bigger. So the whole denominator is getting bigger, which is really getting closer and closer to 0. Here's one you probably have seen before. This is something that you should have seen, I would say, in pre-calculus. Maybe even before that, if you were in Algebra 2, say in high school, you might have seen this. But you should have seen this in pre-calculus. Whether you remember it or not, this doesn't really matter. But this is a pretty important one. This function right here is a fairly important function when it comes to talking about compound interest. And what ultimately happens here is this limit is the definition of e, that natural exponential number. And it arises from the continually compounded interest formula, where you compound your interest infinitely many times over the course of a period. If you don't remember that, you could look it up. Continually compounded interest. You can go back and look at some of my videos from pre-calculus if you wanted to, where I talk about it. But right now, you never really proved why this equals e, because you need to know how to do limits. You did it mainly, if you saw this in pre-calc, what you probably would have done is a table. And you would have said, okay, here's x, here's 1 plus 1 over x to the x. Let's let x equal 1. What do we get here? Well, we're going to get 2. Let's let x equal 10. Let's let x equal 100. Let's let x equal 1,000,000, right? What do we get when we plug those x's in here? What kind of answer do we get? And what happens is you see that the answer keeps getting closer and closer to 2.71828, etc. And what you're doing is you're letting x go to infinity. Really, I mean, this is the crude way of doing it by making a table, but that's what you were doing. But that's all you had available to you in pre-calc. Well, we're going to do it the right way. We're going to do it now using calculus and L'Hopital's rule. So, first, let's do it this way first. Let's look at the function. As x gets closer to infinity, this fraction right here gets closer and closer to 0. This gets closer and closer to infinity. So this whole thing is going to get closer and closer to 1 plus 0 to the infinity, or 1 to the infinity. But if you remember back to that list of indeterminate forms I showed you at the beginning of this lesson, this thing right here is indeterminate. Okay? So we need to try and apply L'Hopital's rule, but this isn't a fraction. So what we need to do is we need to somehow write this as a fraction. Now, it's not as simple as the last one where you can just make an exponent change from negative to positive or vice versa. What you need to do is we need to use logarithms. Now, the primary reason why we need to use logarithms, which you would have learned when you started talking about something called logarithmic differentiation, is because the variable is in the base and the exponent. X is going to infinity, but x appears in the base and the exponent at the same time. Whenever you see that, usually you're going to think about using logs in some way. All right, so the way I'm going to do this is this. I'm going to pull this thing out. I'm going to look at this function. I'm going to say this is y. And ultimately, what I'm trying to do is I'm trying to find the limit as x approaches infinity of y, right? This is what I want to do. I want to find the limit as x approaches infinity of y. That would be the limit of this function. So, what I'm going to do is now I'm going to work with this function a little bit. First thing I'm going to do is I'm going to take the log of both sides of this equation. Why do I do that? Because log rules will allow me to now take this exponent and bring it out to the front here. So I have the natural log of y equals x times log, sorry about that, times log of 1 plus 1 over x. Okay? Which I can also write as log of 1 plus 1 over x over x to the negative 1. I could also write 1 over x here as x to the negative 1. Right. And this is log y. Then what I can do is I could take the limit as x approaches infinity of both sides. Now, this will be the limit of log y. This will tell me what the limit of log y equals. But I want to know the limit of y, so just keep that in mind. But let's look at what we have, okay? We'll eventually loop it back to this one. So, as x goes to infinity, this thing goes closer to 0. This whole inside gets closer and closer to 1. The log of 1 is 0. So the numerator is going to get closer and closer to 0. Remember, this right here is 1 over x. And as x goes to infinity here, the whole fraction goes to 0. So this fraction is getting closer and closer and closer to 0 over 0, which is an indeterminate form. But it's also a fractional indeterminate form, so L'Hopital's rule. So what are we going to do? What we're going to do is, in order to do the limit as x approaches infinity of this, we're going to take the derivative of the numerator and the derivative of the denominator. Now the numerator is a log, so we've got to use our log rule, which is u prime over u. So the derivative of this divided by this, what would that be? It would be negative x to the negative 2 over 1 plus x to the negative 1. And then the derivative of the denominator would be negative x to the negative 2. Now think of this as over 1, so you have a fraction divided by a fraction, you flip and multiply. What happens is that these two x to negative 2's cancel. So now what do I have? I have the limit as x approaches infinity of 1 over 1 plus x to the negative 1. Well, remember, this is 1 over x. So as x goes to infinity, this will stay 1, this will stay 1, this is getting closer to 0, so I have 1 over 1 plus 0, which is 1. But remember, what was this? This was the limit for log y. So now I just figured out that the limit as x approaches infinity of log y equals 1. How would that help me figure out what this is, which is what I'm looking for? Well, think about it. I introduced a log into this problem. I want to get rid of that log now and just get y by itself. Well, if I look at this, the limit as x approaches infinity of e to the log y, if I raise this function up into the exponent of e, as long as I do it on the other side, we're good. Well, these cancel, giving me just y. So that limit as x approaches infinity of y is going to equal to e to the first. So the answer we were looking for was e to the first, or just e, and therefore you see that this is approaching e, and that's the definition for e, where e comes from. Here's another one where we're going to need logarithms. Again, notice the similarity. X in the base, x in the numerator. In this case, x is going to 0. That's not really the reason why we need logs. The reason why we need logs is what's happening in the function that we're trying to take the limit of. Okay, so I'm going to do the same thing. I'm going to let y equal sine x to the x. And I'm going to take the log of both sides. What this allows me to do is to take this x out to the front. So I end up with log y equals x log of sine x, which ultimately gives me log of sine x over x to the negative 1. Take this, which is x to the first, bring it to the denominator, so now it's x to the negative 1. That's log of y. So then what I'm going to do is I'm going to take the limit I'm having trouble with my pen here. Let's see. So I have a limit as x approaches 0 from the right, and from the right doesn't really mean a whole lot here. It just has to do with this logarithm we end up with of the log of sine x over x to the negative 1. And you see what happens. Well, as x goes close to 0, sine gets close to 0. And the log of something that gets close to 0 actually gets closer to negative infinity. The denominator is going to get closer to positive infinity. And again, just think about the two functions. Here's a logarithm. The thing inside the logarithm as x or whatever, the sine x gets closer and closer to 0. The function itself goes down to negative infinity. And x to negative 1 is this hyperbola. As x gets closer and closer to 0, the function gets closer and closer to positive infinity. The reason why it's from the right ultimately has to do with a little bit of this here. Logs are only defined when x is positive. So, anyway. This is a L'Hopital's rule problem, right? This is an indeterminate form. So, what are we going to do? We're going to apply L'Hopital's rule. So, it's the limit as x approaches 0 from the right of the derivative of the numerator. So, this is, again, logarithm. So, u prime over u. So, this will be cosine x over sine x. The denominator is going to be negative x to negative 2. Now, think about this here. Okay? This right here is the same thing as cotangent. So I could write this as the limit as x approaches 0 from the right of cotan x over negative x to negative 2. Which, if you think about this, is the limit as x approaches 0 from the right of cotan x over negative 1 over x squared. And this, I should have wrote this differently. Cotan is the same thing as 1 over tan. I only do this because usually I think tan is probably easier for people to work with than cotan. But anyway, I have a fraction, divide by fraction, so what I'm going to do, flip and multiply. Finally, what do? I have the limit as x approaches 0 from the right of negative x squared over tan x. Right. And I look at what happens here. As x gets closer and closer to 0, the numerator gets close to 0. Tan of 0 is 0, so that gets closer to 0. What do I got? I got another L'Hopital's rule problem. So I do the limit as x approaches 0 from the right of negative 2x over the root of tan is secant squared. Right, well, here is where we don't have to use L'Hopital's rule anymore. The numerator is going to get closer and closer to 0. The denominator, secant of 0, is actually 1. So that'll be 1 squared. Which 0 over 1 would be 0. And so there we go. But remember, that's not the answer. That's the answer for the limit of log y. So now if I want to do the limit as x approaches 0 from the right of sine x to the x, I have to take the limit of log of sine x to the x and get rid of the log. Well, that means I should do e to whatever this answer over here was. Well, e to the 0 is 1. So if you introduce a log in here, we're going to get rid of it by introducing an e at the end. And there's our answer, 1. Okay, one thing I want to point out, and this is for the last example, is when we look at that limit as x approaches 0 from the right of sine x to the x, I should have looked at what was happening with this function right away. I didn't do that. Right? I just went straight into doing logarithms. But really look at this. As x gets closer to 0, sine of x gets closer and closer to 0. And of course, the numerator is getting closer to 0 because it is just x. So this whole thing's getting closer to 0 to the 0. But 0 to the 0 is one of those indeterminate forms. It's not a quotient indeterminate form, but it is indeterminate. So So that list of indeterminate forms I gave you in the beginning of this lesson is really important. All right, so I just needed to point that out. So let's go back to this one now. As x gets closer and closer to 1, this is going to get closer and closer to natural log of 1, and natural log of 1 is 0. So the denominator is going to get close to 0, which makes the whole fraction get closer and closer to infinity. Same thing's going to happen here, so I'm going to get infinity minus infinity. Now this is important. You know, this behavior of fractions, you got to keep learning this. Think about these fractions, 1 over 10, 1 over 100, 1 over 1,000. As the denominator gets bigger, the whole fraction itself is getting closer and closer to 0, as opposed to 1 over 10, 1 over 100, 1 over 1,000. This denominator, this denominator, this denominator, those denominators are getting smaller. They're getting closer and closer to 0. But what's happening to the whole fraction? Well, you would flip this and multiply, flip this and multiply. So actually this whole fraction is 10. This whole fraction is 100. This whole fraction is 1,000. And what are these getting closer to? Infinity. So if your denominator gets bigger, the whole thing gets close to 0. If your denominator is getting smaller and closer to 0, the whole thing is going to infinity. Something you should have learned in Calc 1, but just to reiterate it. All right. So how are we going to deal with this? This isn't L'Hopital's rule. It's indeterminate, but it's not L'Hopital's rule indeterminate, and that's not a quotient. Well, in order to turn this into a quotient, we're going to do the most simple thing possible. Do the subtraction. So we have the limit as x approaches 1 from the right of common denominator is log x times x minus 1. So this will be x minus 1 minus log x. Now look at what happens here. As x is close to 1, this is getting close to 1, this is 1, this is getting closer and closer to 0, so 1 minus 0, 0 in the top. Denominator, this is getting closer and closer to 0, this is getting closer and closer to 0, so 0. Now we're in a quotient indeterminate form, so now we're ready for L'Hopital's rule. So we'll do the derivatives. The limit as x approaches 1 from the right of the derivative of x is 1, derivative of 1 is 0, derivative of log x is 1 over x. Here we're going to need product rule, so I'm going to go 1 over x times x minus 1 plus log x times the derivative of x minus 1 is 1. And we're going to look at this limit. Now this limit is kind of a mess, right? We have fractions inside fractions, so we really should clear this up. So what I'm going to do is fix this fraction. This is going to become one fraction, so that's going to be x minus 1 all over x. That's common denominator. Just essentially write this as x over x. So x over x minus 1 over x. Here, this is over x, right? This has to become over x, so I'll multiply by x over x. And so what I'm going to get is x minus 1 plus log x all over x. Now I have a fraction divide by fraction. I'll flip and multiply. That'll cancel these two x's and ultimately give me the limit as x approaches 1 from the right of x minus 1 over x minus 1 plus log x. All right. That makes things a little bit easier. Okay. Oh, sorry, I mixed something. Remember, I had to multiply by x, so there's actually an x here, and there's an x here. There we go. All right. So now, as x gets closer and closer and closer to 1, what's going to happen here? Well, remember, it's 1 from the right. Okay? So as x gets closer and closer to 1 from the right, what you're going to get is 0 on the top. And this will be 0 times 1 times 0, which is 0 also. What you get is another L'Hopital's rule problem. Alright, so what are we going to do? We're going to apply L'Hopital's rule. So the limit as x approaches 1 from the right of the derivative of the top will just be 1 now. And the derivative of the denominator is going to be 1 minus 0. Now I need another product rule to handle this one. So that'll be log x plus x times 1 over x. And so now look at what happens as x gets closer to 1. Well, I could simplify this, but at this point, this is a 1, this is a 1. This is going to get closer to log 1, which is 0, and this will be 1 over 1. So what do I get? I get 1 plus 1 plus 1, 1 over 1 plus 1 is going to give me 1/2. And so, ultimately, that limit is a half. So you see, infinity minus infinity, not equal to 0. In this case, that was equal to a half. In another case, it could be equal to anything else. Okay, all that being said, we saw some indeterminate forms. 0 over 0, infinity over infinity, 1 to the infinity, 0 to the 0. What other ones did we see? We saw 0 times infinity, infinity minus infinity. These were all indeterminate. There are some things that look like that, but are actually determinate. You can actually find the value, so don't get fooled. Here, infinity plus infinity is infinity. A really large value plus another really large value gives you an even larger value. Okay? This negative infinity minus infinity is really the same thing, just in the opposite direction. So negative infinity, 0 to the infinity as opposed to 0 to the 0 gets closer and closer to 0, and 0 to the negative infinity, infinity. Basically, these are opposites of each other, just like the fractions I showed you. Denominator gets big, numerator the whole thing gets small, vice versa. So these are determinate. They look similar to these, so you're going to have to make sure you keep your eye out for which ones are indeterminate and which ones are determinate. And when it comes to L'Hopital's rule, out of all these, the only ones you can actually directly apply L'Hopital's rule to are the fractional ones here. Okay? We can eventually get all these to become fractional forms, but the only ones you can apply it to is there. And if it's not indeterminate, do not apply L'Hopital's rule. If I had a limit like this, limit as x approaches 2 of x plus 5 over x minus 7, okay? This is not indeterminate. Okay? If x is getting closer and closer to 2, the numerator is getting closer and closer to 7, the denominator is getting closer and closer to negative 5, and so the whole thing is just getting closer and closer to 7 over negative 5. There's no L'Hopital's rule involved. This is just plug the number in, you're good to go. If I applied L'Hopital's rule to this, I would get the wrong answer. Because if I apply L'Hopital's rule to it, when I shouldn't, and I take the derivative of the numerator, derivative of the denominator, I'm going to get 1, and say, well, the limit is 1. Well, the limit is not 1. So make sure you apply L'Hopital's rule only when it applies, and it applies to these two fractional forms.